right, so we left off talking about other aromatic compounds, and we talked about what the criteria were for a compound to be aromatic, and that it has to have a fully conjugated ring with overlapping p orbitals. It's got to meet Huckel's rule. It means it's got to have an odd number of electron pairs, or 4n plus 2 total pi electrons, where n is an integer, 0, 1, 2, 3, 4, etc. When we have an anti-aromatic compound, we're going to have a fully conjugated ring with overlapping p orbitals and an even number of electron pairs, where we have 4n total pi electrons, okay? And where n is an integer, 0, 1, 2, 3, 4. When a compound fails criteria number 1, so when it doesn't have a continuously overlapping system of p orbitals, it is considered to be non-aromatic. And I also added to that in that a compound will do anything it can to avoid being anti-aromatic. And that's why cyclobutadiene adopts the rectangle shape and cyclooctatetraene adopts a tub shape because they avoid being anti-aromatic. Well, let's move on and talk about some other annulenes, because an annuline is a ring that's fully conjugated. And you can see here that we have 6-annuline, which is essentially benzene. And you know that benzene is an aromatic compound, right? It has an odd number of electron pairs, 1, 2, 3. It has a fully conjugated system of, or a continuously overlapping system of p orbitals. However, in 10-annuline, when you look at that, you have 1, 2, 3, 4, 5. So we have an odd number of electron pairs. It also fulfills Huckel's number, 4n plus 2, where n is equal to 1, right? 4 times 1 is, or sorry, when n is equal to 2. So 4 times 2 is 8, plus 2 is 10, and we have 10 pi electrons in here. However, the problem with 10-annuline is that it's actually a non-aromatic compound. So benzene is aromatic, okay? 10-annuline is non-aromatic, and the reason why is because the hydrogen here and the hydrogen here, they actually cause a steric interference with each other. And what it does is it pushes the ring out of planarity. So instead of having that continuously overlapping system of p orbitals, it causes it to be non-planar. And so since you break that overlapping system of p orbitals, this compound is in fact non-aromatic, okay? Because you've broken that continuously overlapping system of p orbitals. Now with 14-annuline, if you count out the total number 1, 2, 3, 4, 5, 6, 7. So we have 7 pairs. So that's an odd number of pairs of pi electrons in terms of the Huckel number. 7 times 2 is 14. So if n is equal to 3, 4 times 3 is 12, plus 2 is 14. So you would think this would be an aromatic compound, and in fact it is, okay? Now, are there hydrogens like here and here and here and here? Yes, there are. However, the ring is big enough that the steric hindrance is very little. And so 14-annuline actually remains planar. And so it is an aromatic compound. So to summarize, 6-annuline or benzene and 14-annuline, those are aromatic compounds, whereas 10-annuline is a non-aromatic compound because of the steric hindrance here from these 2 hydrogens inside the ring. Now, aromatic rings can contain carbanions and carbocations, and I alluded to that earlier during today's lecture. Let's say you have a 5-membered ring. In a 5-membered ring, you've got 3 bonding molecular orbitals, and they can accommodate a total of 6 pi electrons. Well, 6 pi electrons is a Huckel number, right? 4n plus 2, where n is equal to 1. So if I look at this molecule here, cyclopentadiene, you can see that this is a non-aromatic compound. Why would this compound be non-aromatic? Because all 4 of these carbons are sp2 hybridized. However, this carbon that I'm going to highlight in green, it's sp3 hybridized, isn't it? So this does not have a continuously overlapping system of p orbitals. However, there are 2 hydrogens there, aren't there? All right, if I take the cyclopentadiene molecule, there are 2 hydrogens here. And if I deprotonate it so that I end up with the cyclopentadienyl anion, so I have a negative charge here, right? Oops, can fix that bond a little bit. What's going to happen is that instead of this carbon being sp3 hybridized, what it's going to do is it's going to adopt sp2 hybridization. Now, why would it do that? Why would this become sp2 hybridized? Okay. The reason why is because if that carbon is sp2, that means it's got an unhybridized p orbital on it. This one does, this one does, this one does, and this one does. Then these two electrons, the lone pair, are actually in the p orbital. So now I've got a continuously overlapping system of p orbitals that you can see here. And how many electrons do I have in the p orbitals? I have 2 from the lone pair. I also have 3, 4, 5, 6. If I have, look, 1, 2, 3, 4, 5, 6. I have a Huckel number, right? 4n plus 2, and n is equal to 1. I have that closed shell electron configuration. All the electrons are in bonding molecular orbitals. And that explains why the cyclopentadienyl anion is aromatic. It's actually an aromatic anion. So we don't necessarily have to have a neutral compound in order for it to be aromatic. Now, what's the consequence of this is that explains why the pKa of the hydrogens in the cyclopentadiene molecule are, why the pKa is so low. If you think about a hydrocarbon, something that's made of only carbon and hydrogen like this, up until now, we considered the pKa's of hydrocarbons really high, at least over 40, at a minimum over 40, okay? Unless we're dealing with an alkyne, but that's neither here nor there right now. And so you can see the pKa is really low. Why is it so low? And this would be a good quiz question. The reason why it's so low is because once you deprotonate it, you go from something that is non-aromatic to something that is aromatic. And it has greater stability. Now, what if we have a 7-membered ring? Okay? What if you have a 7-membered ring? If I just draw this molecule here, if I draw a cycloheptane ring, and I put 1, 2, 3 double bonds, that would be 1,3,5 cycloheptatriene. Well, that's a non-aromatic compound. Why is that non-aromatic? Because it doesn't have a continuously overlapping system of p orbitals, right? This carbon is sp3 hybridized. Therefore, again, this is non-aromatic. What if I take one of those protons and I remove it, right? What if this behaves as an acid and it donates a proton? Let me just copy it because I hate drawing 7-membered rings. So I'm just going to copy that and I'll throw it over here. Okay. So if this donates one of its protons, it's here. So I end up with a cation. Let's draw it here. Give me a sec. Go. So we have a carbocation. Now, this carbon, it's sp2 hybridized, isn't it? What does that mean? It's got a p orbital. Now I've got a continuously overlapping system of p orbitals. And I have a total of how many pi electrons? 1, 2, 3, 4, 5, 6. That's a Huckel number. So I fit the criteria, or this molecule, or this ion, rather, fits the criteria for being aromatic, right? I've got the total of 6 electrons in the ring. 1, 2, 3, 4, 5, 6. So there you go. Now I have a closed shell electron configuration. So that explains why this ion that we call the tropylium ion, or the tropylium cation, and you need to know its name, is an aromatic cation. It actually has 7 resonance structures, which is pretty cool. So 7 resonance structures. And you should be able to draw them all. Anyhow, there you go. So now we've just shown how not only this cation, but also this anion, why these two ions are aromatic. Okay, using the rule for a compound being aromatic. It's got to have a continuously overlapping system of p orbitals, and it has to have a Huckel number of electrons. Let's look at some other examples. Again, going back to the introduction slide today, I showed you a bunch of heterocycles, meaning compounds that don't only contain carbon in the ring. And I told you that they were aromatic. What about these compounds here, pyridine and pyrrole? They're both aromatic. However, they're aromatic for kind of different reasons. On the pyridine nitrogen, there's a lone pair of electrons, and on the pyrrole, there's a lone pair of electrons. However, the lone pair on the nitrogen is sp2 hybridized. That goes all the way back to Organic Chemistry 1, way back at the beginning. In fact, this is chapter 1 of Organic Chemistry 1. That lone pair is in an sp2 hybridized orbital. What does that mean? That means you've already got the p orbital here, right? And you have a continuously overlapping system of p orbitals in the pyridine molecule. Each one has an electron. So we have 1, 2, 3, 4, 5, 6. That's a Huckel number of electrons. It's a closed ring. It's a continuously overlapping system of p orbitals. So the lone pair has nothing to do with the compound being aromatic at all. However, in pyrrole, the picture is quite a bit different. If you look at the lone pair in pyrrole, it's actually in a p orbital. Okay? This nitrogen, you might look at it and say, well, come on, it's got a steric number of 3. 1, 2, 3, 4. Shouldn't it be sp3 hybridized? Well, here's the news. It's not sp3 hybridized. Okay? The lone pair, if it can go into a p orbital so that it will render the molecule aromatic, it will do it. Okay, a molecule will do whatever it can to avoid being anti-aromatic, and it will do whatever it can to be aromatic. So if we put that pair of electrons in a p orbital and we make the hybridization here sp2, well, then what do we have? We have a continuously overlapping system of p orbitals, and we have a total of 1, 2, 3, 4, 5, 6 electrons in that continuously overlapping system of p orbitals. That's a Huckel number. So again, both of these molecules, pyridine and pyrrole, they are both aromatic. However, the reasoning is quite a bit different. The lone pair on the nitrogen in pyridine is not involved in aromaticity. However, the lone pair here goes into a p orbital to render pyrrole an aromatic molecule. Kind of interesting, huh? And these are specific examples that you need to know. Again, the heteroatom's lone pair is necessary for aromaticity. And if it is necessary, it's going to be included in the Huckel number of pi electrons. This is just a politically correct way of saying that the lone pair will do whatever it's got to do to render the molecule aromatic. Now, what are some other consequences of all of this? Okay, when the lone pair is required for aromaticity, then the lone pair isn't going to be basic, is it? Right, let's go back to our pyridine. I told you already that this lone pair is not required for aromaticity. Therefore, pyridine makes a great base, okay? It's a wonderful base. If you protonate it, the pyridinium ion has a pK of around 5, so it's still aromatic. If you protonate the pyrrole molecule, though, whoa, you get something that is non-aromatic. It doesn't have a continuously overlapping system of p orbitals because now this nitrogen is sp3 hybridized, but it's got a really low pK. It's really acidic. Why? It's 10 to the power of 5 more times acidic. What's that? 100,000 times more acidic than the pyridinium ion. Why? Because if it donates that proton, it's going to go back here and become aromatic. So if you look at the electrostatic potential maps of pyridine and pyrrole, you see quite a different picture for the two of them. You see that lone pair on the nitrogen in pyridine is localized. You see all the electron density around here, whereas in pyrrole, here's our nitrogen, but we see that the electron density is spread around the ring, and I mean the nitrogen lone pair electron density isn't localized on that nitrogen. Why? Because the lone pair on the nitrogen is actually participating in aromaticity. Okay, it's delocalized throughout the ring, whereas again, the lone pair on the nitrogen in pyridine is localized. It has nothing to do with aromaticity at all. So make sure you understand why these two molecules are aromatic, but how different they are. That the lone pair in pyridine has nothing to do with aromaticity. It is not involved in the molecule being aromatic. However, in pyrrole, this lone pair is saying, you know what, man, I'm going to jump into p orbital because if I do, then I'll be aromatic. I'll be an aromatic compound. What's an aromatic compound? It's a compound that's stable, right? It has extra stability. Well, with that in mind, let's take a look at some examples. And you can imagine how these lend themselves very easily to a multiple choice question for your next quiz. And it simply asks us to determine whether the following ions, whether they're aromatic, non-aromatic, or anti-aromatic. So we'll call them aromatic, non-aromatic, or anti-aromatic. I'm going to help walk you through the first ones here. So if I take a look at the first molecule, I have this, well, let me zoom out a little bit. I have a three-membered ring. Okay, I have a three-membered ring. I have sp2 hybridized carbons here and here. Okay, and if I have a continuously overlapping system of p orbitals, right, if this is a p orbital here, okay, well, then I've got 2 electrons in there. Then what's my Huckel number? I've got 1, 2, 3, 4. So this is a non-Huckel number. This is 4n, where n is equal to 1, right? 4 times 1 is 4. And so this compound is anti-aromatic. Anti-aromatic. I guess I was going to use the AA sign for that. So this is an anti-aromatic compound. Again, you can see how this would be a planar molecule. There's no way that this molecule could escape being planar. Let's take a look at B. In B, we also have a continuously overlapping system of p orbitals, sp2, sp2, sp2. But now we have a Huckel number where we have 4n plus 2, where n is equal to 0, right? 0 times 4 is 0, plus 2 gives you 2. And we only have a total of 2 high electrons in the closed system of p orbitals. Therefore, this is an aromatic compound, or an aromatic ion, I should say. With that in mind, could anybody answer C or give me an idea about C? While you do that, I'm going to turn off the heater in my office on this cold Memorial Day. Could anybody give me an idea about C, whether that would be aromatic or anti-aromatic? All carbons in here, all carbons are sp2 hybridized. That means I have a continuously overlapping system of p orbitals, don't I? But how many pairs of electrons do I have in here? I don't have a Huckel number, do I? Because I've only got 1, 2, 3, 4. So I've got 4n, where n is equal to 1, right? 1, 2, 3, 4. Therefore, this is an anti-aromatic compound. Anti-aromatic compound. And for the last one, if I put this pair of electrons in a p orbital, okay, then I'd have a continuously overlapping system of p orbitals. All these different p orbitals here. And then how many pi electrons would I have? Let's count. I'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is a Huckel number, right? 4n plus 2, where n is equal to 2. 4 times 2 is 8, plus 2 is 10. Therefore, this is an aromatic, aromatic ion. So what I want to do before next class is I want you to take the time to determine whether these compounds are aromatic, non-aromatic, or anti-aromatic, and then determine whether the lone pairs are participating in aromaticity or not. For example, are these lone pairs participating in aromaticity? This one, this one, this one. Are any of these lone pairs participating in aromaticity? And we'll take a look at that during our class on Wednesday. Polycyclic aromatic compounds. Our book doesn't go into a lot of detail about polycyclic aromatic compounds, which sometimes they call PAHs, polycyclic aromatic hydrocarbons. Anyhow, these compounds are also aromatic. You can see here that in naphthalene, for example, we have 1, 2, 3, 4, 5 right? Pairs of electrons, so that's an odd number. Here we have 7 pairs. Here we have 7 pairs. So these are also aromatic compounds. What's interesting about the rings in polycyclic aromatic compounds is that not all of the rings have equal energy or equal reactivity. Some of them are more reactive than others, and I probably won't ask you a whole lot about that. All I really want you to know about polycyclic aromatic compounds are how to name them. So you should know naphthalene, anthracene, and phenanthrene, and just be able to identify the structures when you see them. And that brings us to section 17.6, which deals with reactions at the benzylic position. Hopefully by now you know what a benzylic position is, but in case it escapes your memory or has escaped your memory, a benzylic position is basically the position directly attached to an aromatic ring or a benzene ring. So if you have a benzene ring like this, and you have a carbon attached directly to it, those are called benzylic positions, right? If you had another one down here, right, this would be a benzylic position. Okay, so the carbon attached directly to the aromatic ring. Now, if you take an aromatic ring and you treat it with the Jones reagent, so this is sodium dichromate, sulfuric acid, and water, right? It's just a way to make chromic acid, H2CrO4, okay, in situ. Anyhow, nothing happens. The same thing if you take just a hydrocarbon, right? Nothing's going to happen, right? What did we use this reagent for? We used it to oxidize a primary alcohol to a carboxylic acid or a secondary alcohol to a ketone. Well, what's cool is that you can actually oxidize a benzylic position if you've got one. Okay, if you have a benzylic position and it has at least one hydrogen, okay, you've got to have a minimum of one hydrogen. It will oxidize it to a benzoic acid derivative. Okay, so it gets oxidized, and if you're wondering, Mr. Dion, what happened to those 3 carbons? They kind of are what we call excised. Okay, they are just removed, and they end up, in the waste of the reaction, so to speak. Okay. So we end up removing those. Same thing if you had this molecule. This is called cumene. If you were to take this molecule here and you had, only 1 hydrogen here and 2 methyl groups, and you did the same thing, right, you'd end up with the same compound. Okay, so you've got to have at least 1 hydrogen at the benzylic position. If you've got a tertiary group here, you get nothing happening because there's no hydrogen attached to the carbon at the benzylic position. Now, besides using chromic acid, which again is produced by using sodium dichromate. Okay, so sodium dichromate, sulfuric acid, and water. That's one way of oxidizing at the benzylic position, but this is strongly acidic, right? Because you're making chromic acid, you've got sulfuric acid in there for Pete's sake. Of course, it's acidic. You can also do a benzylic oxidation in basic conditions. However, it's a 2-step process. The first step is to treat the molecule with potassium permanganate and water, and you heat that up. That makes a benzoate. Okay, so this is called a benzoate, which is the conjugate base of a carboxylic acid. Then in the second step, you can treat it with dilute aqueous acid to produce the carboxylic acid. So now we got 2 ways to do benzylic oxidation. We can either do it in acid or we can do it in base. In acid, using the Jones reagent, or in base, using this 2-step procedure. Step 1, potassium permanganate, water, and heat. And step 2, hydronium. A benzylic position is kind of like an allylic position, and it is readily available to undergo free radical bromination. If you remember allylic positions, and we talked about allylic bromination quite a bit in chapter 10 in General Chemistry 1, if you remember, and I don't want to reteach that class at the moment, but let's say you have something like this, okay? You've got the vinylic position, then you have the allylic position here. So since we have an allylic hydrogen right here, and this is just a review of chapter 10, okay? If you treated this with NBS, so N-bromosuccinimide, you do the hydrogen abstraction, which produces the radical. So you end up with the allylic radical like this, and there's a resonance contributor. Let me draw that off the top of my head, which looks like this. I'm going to leave out the curved arrows, and then of course you can brominate at either of those positions. So you could brominate here, I should have planned this out a little bit better. Okay, you could brominate there, or you could brominate here. Either way, that's allylic bromination. Okay, well, we can do a benzylic bromination. So if we take a benzylic position that's got a proton, we treat it with NBS and heat, and we can do the bromination like that, right? In the first step, you do the hydrogen abstraction. I'm really getting into the details here, but it's kind of interesting. So after the first step, you do the hydrogen abstraction. Why would that happen so readily? Because you get a resonance stabilized, excuse me, radical, a benzylic radical, and you should be able to draw the resonance structure. So if you don't remember, fishhook arrows, you should be able to draw them. So I'm not going to go over all of them, but you should be able to draw all the resonance contributors here. So I'll just draw the first one, okay, where we have something that looks like this, okay, like that, and then I'll put here, etc. Okay, so you should be able to draw the rest of those. But anyhow, then we do the halogen abstraction, and we end up brominating at the benzylic position. So what other reactions can we do at a benzylic position? Well, you know that we can do an SN1 reaction, right? Because after we lose our leaving group, right, which is the first step of an SN1 at a time, so to speak, you would end up with what? A benzylic what? Carbocation. Of course, that's resonance stabilized, isn't it? Right? You should be able to draw all the resonance contributors for that. So then water can come in and act as a nucleophile. Then you do a proton transfer, and you end up with this benzyl alcohol derivative. If you have an unhindered benzoic bromide, that can undergo an SN2 reaction. Remember this compound here? This is called benzyl bromide. Benzyl bromide. It's a very commonly used electrophile in organic chemistry to add a benzyl group to something. So that's just going to undergo an SN2 reaction. This is kind of just a review of things that you already learned way back in chapter 7 in Organic Chemistry 1 when we discussed what? SN1, SN2, E1, E2 reactions. And so there's some other cool reactions. What about E1 and E2 reactions, right? You could do an elimination reaction here with sodium ethoxide, and you should be able to draw the curved arrows for this. You draw the ethoxide ion like that, and then you should be able to draw the curved arrows for the elimination like this. And the reason why this is going to occur so readily is now you end up with a fully conjugated system, right? It alternates double, single, double, single, double, single, like that. So you end up with something that's highly stable. Also, you've learned E1 elimination, right? Where in the first step, you convert this into a good leaving group. So once you've converted that into a good leaving group, it will leave. Then you end up forming the benzylic carbocation upon treatment with sulfuric acid, right? And then then you can do the elimination. So you end up removing a proton. I'm not going to draw the entire mechanism, but anyhow, you could finish that one up like that, okay? You end up with a fully conjugated system there. All right, and again, this is just review. These last few reactions are only review. And so that gives us all of these different reactions here, right? We could either start with toluene, and we could do a free radical bromination, or we could start with this molecule. This is an isopropyl benzene. You could call it that. It's also called cumene. So cumene, I don't think they ask you to memorize it in the book, and I don't expect you to remember it. But cumene is a common organic compound. You could do a benzylic bromination of that. Of course, since both of these have benzylic protons, you could oxidize them in acid or base to benzoic acid. You could do SN1 or SN2 reactions on a primary alkyl bromide. You could do E1 or E2 on a tertiary. You could do an SN1, then you could do E1. You could do all kinds of stuff. But look at this. You guys know, because you're Organic Chemistry 2 students, this is fresh in your brain. If you've got an alcohol, holy smokes, you got the whole world, the world is your oyster, right? Here you could take that primary alcohol, you could oxidize it, you could do a Grignard, you could oxidize it again, you could do a Williamson ether synthesis. Give me an alkene, right? I can control the whole world. I could do a bromination. I could do a dihydroxylation. I could do a Markovnikov, anti-Markovnikov addition. And this is the way you want to think in organic chemistry too. What can I do with this functional group? And you can do a lot of different things with all of these different functional groups. So with that in mind, let's take a look at a problem here. It just says, simply draw what happens when each of the following compounds is oxidized with chromic acid. So we'll put here sodium dichromate, sulfuric acid, and water. And could anybody name the compound that would be formed in this oxidation, the first one? Could anybody name the compound that's formed after the first reaction? The reaction arrow I have drawn in black ink. Could anybody name? Yeah, it's benzoic acid, absolutely, right? Because we have one benzylic position, so we're going to end up making this compound, right? We're going to make this, which is benzoic acid. The next one, we have two benzylic positions here. So we're going to end up with two carboxyl groups, aren't we? We're going to have one over here, and we're also going to have one over here. I don't expect you to memorize the name of this one, but this is called isophthalic acid. So let's see if I can spell it. Isophthalic acid. And then the last one, if I do, I'll just copy and paste this. So copy and paste this guy. How many benzylic positions can I oxidize at this third molecule, the very last one? The one that I have in the yellow circle. How many benzylic positions can be oxidized? Could anybody tell me? Yeah, absolutely. Right? Only two. So we'll take the green arrow we'll put here. Cannot be oxidized since no benzylic hydrogen. So what am I going to end up with? I'm going to have my aromatic ring. I'm going to have that tert-butyl group, which is going to remain completely untouched, like that. Then I'm going to oxidize here, and I'm also going to oxidize over here in the two positions that do have benzylic protons. And that is it, my friends. There you go. So that's how you do reactions at the benzylic position.